Welcome. This course covers common agent architectures: React, Plan and Execute, Reflection, and LATS.
An architecture is the structural pattern that governs how an LLM thinks, acts, and corrects itself across turns. Autonomy spans a spectrum, from simple single-prompt completion on the left to tree search multi-agent loops on the right. Every design balances a triad: latency or speed, cost or token use, and accuracy or reasoning depth. Some patterns interleave thought and action. Others separate planning from execution with a full step list first. Without architectural structure, naive single-turn models often fail at complex multi-step reasoning. React feels like fast impulse action. Plan and Execute is deliberate upfront planning. Reflection is post-mortem learning. Architectural selection also determines system reliability and whether a product can meet enterprise SLAs. Section 1 Takeaways. Architectures define reasoning structure, balance speed, cost, and accuracy, and matching pattern to domain prevents compounding errors. Pause here. Architecture is a deliberate design choice with unavoidable trade-offs. Now the quick check. Quick check after Section 1. What triad of trade-offs should architecture selection balance? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 2 covers the React pattern: reasoning plus acting through interleaved thought, action, and observation. The core React cycle is thought, then action, then observation, then thought again. In thought, the model writes an internal monologue. For example, I need to search for the user's flight status first. In action, the model emits a structured tool call, such as searching flight UA123 through an API gateway. In observation, the system captures the API response, such as a 2-hour delay, and appends it to context. React's strength is real-time adaptability. The agent can change trajectory immediately based on intermediate observations. A primary weakness is token drift. Repeating full history each step inflates context size, cost, and latency. React fits interactive exploration, unstructured search, real-time troubleshooting, and other unpredictable settings. Section 2 Takeaways. React interleaves reasoning and tools, adapts well to feedback, but can bloat context and loop. Pause here. React thinks and acts in turns, and that adaptability has a token cost. Now the quick check. Quick check after Section 2. Which sequence best describes the React pattern cycle? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 3 covers Plan and Execute. A planner brain creates the roadmap, then workers execute the steps. In a decoupled workflow, The planner generates a complete step list before any tool is executed.
Macro planning often creates a structured, directed acyclic graph of subtasks before execution begins.
During execution, a faster, smaller worker model runs steps sequentially in clean isolation. When steps have no interdependencies, plan and execute can run them in parallel and save time. If a step fails, state returns to the planner so it can generate an updated recovery plan. Compared with React, plan and execute often uses far fewer tokens because workers receive only their assigned step. It fits deterministic pipelines, report generation, data extraction, and structured coding tasks. Section 3 Takeaways. Separate planning from execution. Save tokens with parallel workers and replan only on errors. Pause here. Plan first, then execute with focused workers. Now the quick check.
Quick check after Section 3. What is a major efficiency benefit of plan and execute over React? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 4 covers reflection and self-correction. The agent evaluates itself, stores verbal feedback, and improves. Verbal reflection means the agent evaluates its output, writes explicit diagnostic feedback, and stores it in memory. Reflection combines 3 parts: an actor, an evaluator, and a self-reflection buffer for verbal feedback. On attempt 1, the actor generates code. The evaluator catches a unit test failure and validation fails. The reflection model analyzes the stack trace and writes feedback, for example, forgetting null array handling. On attempt 2, the actor reuses that reflection, fixes the null handling error, and passes the tests. Reflections can also live in long-term episodic memory, so future tasks learn from past mistakes. Reflection costs extra LLM calls per step, so use it when correctness matters more than speed. Section 4 Takeaways: verbal self-critique, actor, evaluator, and memory, and strong gains on coding and math. Pause here. Critique before you regenerate, and memory turns failure into signal. Now the quick check. Quick check after Section 4. What key component differentiates reflection from standard retry prompts? Choose A, B, C, or D. Take 1 minute to think. Then choose A, B, C, or D. The correct answer is not shown. Section 5 covers advanced search with LATS and tree-based reasoning across scored candidate paths. Tree methods move beyond linear step-by-step loops by exploring multiple candidate paths at once. LATS unifies Monte Carlo tree search with LLM generation and evaluation. In expansion, the LLM generates alternative action trajectories, such as branches A, B, and C. Candidates are executed and scored. One branch may score 0.9, while another scores only 0.2. Backpropagation reinforces high-scoring paths and prunes poor ones to avoid wasted resources. React follows one path. Tree of thought branches thoughts. LATS adds tool actions plus tree search.
Use tree search selectively for high-stakes domains because latency and compute cost rise sharply.
Section 5 takeaways. LATS combines tree search with LLMs, explores and prunes branches, and maximizes accuracy for hard tasks.
Pause here. Search explores many futures, and scoring decides what survives. Now the quick check. Quick check after Section 5. Which advanced architecture merges Monte Carlo tree search with LLM action generation? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 6 covers a selection framework, hybrid architectures, and how patterns work together in production.
Start with the comparative matrix across React, Plan and Execute, Reflection, and LATS for speed, cost, and accuracy. Decision Rule 1. When uncertainty is high and steps are short, choose React. Decision Rule 2. When uncertainty is low and steps are large, choose Plan and Execute. Decision Rule 3. When accuracy matters and outputs are verifiable, choose Reflection. Decision Rule 4. For complex combinatorial search spaces, choose LATS. Hybrids often use Plan and Execute for macro routing and React inside individual step modules.
State graph engines such as LangGraph combine patterns and can fall back from Plan and Execute to React when failures spike.
Section 6 takeaways. Match pattern to domain, combine macro planning with micro React, and use graph engines for transitions.
Pause here. Selection rules guide design, and hybrids unlock production systems. Now the final section check.
Quick check after Section 6. How can a hybrid architecture optimize performance? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
You completed a quick check after every section. You can now match agent architectures to task constraints with confidence.
Congratulations! You completed Common Agent Architectures. Thanks for watching.